Today we're going to conclude our discussion that we started in the last video, talking about the inductance of a single-phase circuit. In the last video we derived the equation for the flux linkages, and we're going to use that to derive the equation for the inductance. So a quick recap. Again, if you haven't seen the last video, please do go ahead and see that. As a matter of fact, I'll encourage you to see the whole series of videos on inductance of a circuit if you want to completely understand this concept. So just doing a quick recap from the last video. Actually, this goes back to even before, but I'll be using this again today. So I just thought I'd mention this. Inductance we know is flux linkages over the current through that conductor. But in the last video, we considered composite conductors forming a single phase circuit. So we had conductor X with current I flowing, let's say, into the screen, and conductor Y with current flowing out of the screen. Therefore, I've said negative I. Now, conductor X had strands 1 through N, and conductor Y had strands 1 prime through M. What we said was the two conditions we put forth before our discussion was that these strands have to be cylindrical, because all the formulas we've been using are for cylindrical conductors. And so we said the strands would be cylindrical and they would share the current equally. Therefore, in conductor X, each strand would have a current of 1 by n amps per strand, and in conductor Y we would have negative I by m amps per strand. What we then derived was the flux linkages for any strand K could be given as 2 into 10 to the power minus 7 I ln of, and we saw this capital pi being the product function, similar to how sigma is the summation function. So we said that would be ln of a product of dmk. This is basically, in the numerator you have a product of all the distances from that strand to in conductor X to all these strands in conductor Y. So the numerator is all the distances from this strand in X to all the different strands in Y, and in the denominator you had the distance of that strand to all the different strands in the same conductor in conductor X. This was raised to the power 1 by m, and this was raised to the power 1 by n. So let's begin from that as a basis. As I mentioned, L is lambda by I, we know that. So what we can say is L of k would be nothing but lambda of k over I of k. Now what is I of k? The current in strand k is nothing but I of n, the total current I in the conductor X divided by n strands. So we can write that as lambda k over I divided by n. If we put this equation in the numerator for lambda k, I and I cancel out and n comes to the numerator. So we have 2 into 10 to the power minus 7 times n times ln, and you have the product of m going from 1 prime to m d of mk to the power 1 by m over product of n from 1 to n d of nk to the power 1 over n, and all of this is in the long function. So you've defined Lk. So what you've defined is the inductance for any strand K within conductor X. But what we have to realize here is, in this conductor X, and you can see that from this formulation, L1 is not equal to L2, is not equal to L3, and so on, all the way equal, or rather not equal to L of n. So what I'm trying to say is the inductance of all of these strands, though they're in conductor X, individually they're not all equal. And why is that so? You can see that from here. The distance for each of these strands to each of the other strands, let's say in conductor Y or between conductor X, is going to be different. Therefore, this product function is going to come out to be different. Therefore, L of k for each value of k is going to be different. Therefore, the inductances is not the same. But what we do have is, we can say the average inductance is the summation of all the inductances over n. This is nothing but an average function. You have n number of values, you sum them up and divide them by n, and you have the average inductance. What we can then say is that L of x, since all of these are electrically parallel, is 1 by n times L average. Now, the easiest way I can find to give you kind of an explanation of why this is if you imagine an electrical circuit with parallel impedances. So you have Z1, Z2. Let me just draw that properly for you so you see that clearly. So there are three parallel impedances. So there's Z1, there is Z2, and then there is Z3. The average impedance is going to be Z1 plus Z2 plus Z3 divided by 3. This circuit, we can say approximately, is going to be or can be shown as Z average. This is not entirely true, but this is just a rough explanation of why we are doing what we are. So in this case, the total impedance is this, and therefore Z of total is Z average by 3. And that's kind of what we're saying here. Since all of these are in parallel, your L of x, your total inductance, is 1 by n times the average. Now, if we break that out, what that means is 1 by n times, we substitute this, L1 plus L2 plus so on all the way up to Ln divided by n. This is nothing but a summation of Lk, k going from 1 to n. Now we know Lk is defined by this. If you've seen the earlier videos now, you realize when we sum ln values, we can substitute them by the product. Instead of summing ln A plus ln B, we can say ln A of B. So we're going to do exactly that here. And what that's going to give us is L of x is going to be 2 into 10 to the power minus 7 divided by n square, that's this n square, times, if we refer back up here, if we go back up here, that's that n. So 2 into 10 to the power minus 7, n square, n, ln of L1 plus L2 plus so on. And I'm not going to add the lns, I'm going to do a product of those. So we're going to have D1 1 prime, D1 2 prime, so on all the way up to D1m. This to the power 1 by m. Then we're going to have D2 1 prime, D2 2 prime, so on all the way up to, actually let me write this down here so I can write it all in one line and it's not confusing to you. Or rather, let me just delete this now that you've understood the explanation here. Let me just delete this and create some space. And then we'll just write this in one line. So what that implies is that L of x is equal to 1 by n square, or rather we'll put the 2 into 10 to the power minus 7 from here. 2 into 10 to the power minus 7 n square times that n times ln. I am now expanding this term. So for k equal to 1, that's going to be d of 1 prime 1, d of, or rather 1 1 prime, d of 1 2 prime, so on. Just to make this a little bit easier for you to understand, let's substitute this k and m. Let's write it the other way, and then it'll be absolutely clear to you. So then this becomes d, let's say km, and here let's write it as kn. It doesn't matter how, in what order you write them in. So if you imagine k being equal to 1, then you have this as d11 prime, d12 prime, so on. So we'll write L1, then we'll write for L2, and instead of adding them, as I mentioned, ln AF plus B becomes ln AB. So then we would get the values as d11 prime, d12 prime, all the way up to d1m to the power 1 by m. That's for L1. Then for L2, you have 2 1 prime, 2 2 prime, all the way up to d2m 1 to the power 1 by m, and you'll have this all the way up to dn1 prime, dn2 prime, so on till dnm 1 to the power m. This is for ln. All the summations have become products because of the ln, divided by all the distances within conductor x. So you'll have d11, d12, so on all the way up to d1n to the power of 1 by n, so on for strand 2, all the way up to d2n to the power 1 by n. Similarly for strand n, all the way till dnn 1 by n. This n cancels the square out. Now in the next step, what I'm going to do is this 1 by n can be brought in. You remember the identity we talked about last time? We said a of ln b can be written as ln of b to the power a. So the 1 by n will be brought inside. So, and then we will write it together as another summation like I showed you last time. 2 into 10 to the power minus 7 ln of, and you'll have a product for k equal to 1 to n, and in the numerator you have the product for m going from 1 prime to m, dk of m 1 over mn. Now this is 1 over m, and this 1 over n comes in, and then in the denominator you will have a product from 1 to n, dk of n 1 over n square, and all of this is in the bracket for ln. This, as I mentioned last time, if any of you know programming, is a double loop. So you do k equal to 1, and then it goes through all the values for m from 1 prime to m, then k becomes 2, and then it again goes for all the values for m from 1 prime to m, and the same happens in the denominator. So in essence, when you expand this term, you can write this as 2 into 10 to the power minus 7 ln of d11 prime, d12 prime, so on till D1M, and then you have D21 prime, D22 prime, all the way to D2M. All of this goes to D of N1 prime, D of N2 prime, all the way to DNM. All of this to the power of 1 over Mn, and in the denominator you will have D11, D12, all the way to D1n, so on, all the way to dn1, dn2 till dnn, and all of this raised to the power 1 over n square. So that's your Lx value. This top term here is called the geometric mean distance, GMD, and the bottom term in the denominator is called GMR, the geometric mean radius. So what we're going to spell that out as Lx is equal to 2 into 10 to the power minus 7 ln of GMD from conductor X to Y and GMR for conductor X. And this is Henries per meter. Similarly, you have L of Y is equal to 2 into 10 to the power minus 7 ln of GMdx of Y, GMR of Y, Henries per meter. And then you have the total. So this is inductance per conductor, and then you have L, which is Lx plus Ly, Henries per meter, and this is inductance for the circuit. And we move forward from there, so I will just summarize what the GMD and GM. So your GMD X to Y is the geometric mean distance. This is equal to, let me write that, this is equal to product of k going from 1 to n, product of m going from 1 prime to m, dk of m, and the root of mn. This is also sometimes called mutual GMD. And then you have GMR of X is geometric mean radius, also called self GMD in some text, and this is equal to, you have the product of k going from 1 to n and the product of n going from 1 to n, d k of n, and this is to the root of n square. And similarly you'll have GMR y would be equal to product of k going from 1 to m prime, product of m going from 1 to m prime, dk of m, and that will be to the root of m square. So in essence, GMD is nothing but the distance from for all the strands from conductor X to conductor Y, a product of all of them, and GMR, the geometric mean radius, is the product of all the distances for the strands within the conductor. So for X it will be within X, for Y it will be within Y. These formulas will become a lot clearer once I solve some examples in the next video, which I plan to do. So stay tuned for that. If you have any questions, please leave your comments below and do subscribe to our channel. Hope to see you soon, and I'll have the next video up and running very soon for you. Take care. Bye now.